Okay? Good. So we want to discuss one loop amplitudes in today's class. So we completed, we discussed this, the measure issue for closed strings last time. Let me quickly tell you about the similar calculation for open strings. Okay? So suppose we want to do a one loop amplitude for an open string. That's this little string here that runs around in a loop. Okay? So the kind of surface we have is a cylinder. But this side is identified as this. It's a little cylinder. The string is very little. Okay? Now, we could ask how many moduli is a cylinder? Okay? This is the same as the number of zero modes of the B operator that respect the boundary conditions of the cylinder. So what are the boundary conditions of the cylinder? The boundary conditions of the cylinder are periodically in this direction, and at the edges, the boundary conditions we discussed before, namely that B is equal to B. Okay? Now, on a torus, we had two zero modes for the for B and B cylinder, namely constant B and constant B. Okay? We're going to have the same kinds of zero modes here. This can be thought of as part of a torus. With the doubling trick, it becomes a torus. Okay? So we're going to have the same zero modes, except that B and B cylinder are not independent zero modes, because B is equal to B cylinder at the boundaries. Okay?
If the boundaries are lower than the upper boundaries.
No. Well, it's still either way, it doesn't matter. But I'm thinking of this little string going around this way. So these are the endpoints. Of course, there's symmetry, right? You could think of it. It doesn't matter. So that's not the reality. Okay, so I'm thinking this is sigma. Okay. Fine. So there's one modulus in this situation. What's that one modulus? That one modulus is really clear. It's the height of this. So suppose we always choose this to be 0 to pi, the sigma direction. This direction is, let's say, tau. We probably want to call it t times 2 pi to be consistent with our notation for the closed string. And the modulus is simply the value of t. Okay? So that's the unique modulus of the game.
What does the angle matter?
You see, we want the angle is fixed by boundary. You see, the boundary conditions we're putting are at the edges del sigma of x is equal to 0. If you change the angle, then you'll have to put different boundary conditions. Okay? So this with del sigma x equals 0. Okay? You can't change the angle. And if you change the angle, you change the boundary conditions. That's not a symmetry. Okay? Good. So the modulus here is this t. Okay. Now, once again, we want to calculate the measure of moduli space. So it's the same calculation we had before. As we'd seen last time, del g zz, if you remember, del g zz divided by del tau bar, I think it was equal to, was proportional to 1 by n tau, and del g z bar by del tau was proportional to 1 by. This is what we saw last time for the torus. Okay? Now what are we doing here? What we're doing here is basically the same as the special case of the rectangular torus. Okay? So in this particular case, we do more or less the same calculation, except we focus it at tau equals I time imaginary part of tau is equal to it. Okay? And because the torus is rectangular, so because our metric always takes the form ds squared is equal to d sigma 1 squared plus tau squared times d sigma 2 squared. What happens, basically all we're changing is gy1. when we change t, the infinite decimal changes in gyy, and gyy has equal components of gzz and gz bar z bar. Is this clear? Okay, it doesn't look clear anyway, but that's not it. Okay, so the question we're asking is, suppose we had the z coordinate, and we have dz bar is equal to, so the metric is equal to ds squared dz bar, where sigma is equal to, belongs to the range 0 to pi, and tau belongs to, as a periodic coordinate in 0 to 2 pi. Okay? Now we're going to go to a new where, suppose we take t2. So this is a general set. Now we work with a variable w such that ds squared is equal to dw. Okay? And these ranges where sigma is the same as above, but tau belongs to 0 to 2 pi t plus delta. Okay? We're now going to take this metric and reword it in terms of the metric, in terms of the variable z, where the periodicities of z, I'm sorry, to be consistent with the notation we used last time, we call this dz, just forget what it's like. Okay? Where we reword in terms of the variable w, where the periodicities of w were that of 0 to tau, 0 to 2 pi t, without the difference. Okay? So what's the change that we have to do? The change that we have to do is real z is equal to real part of w. So the imaginary part of z, okay, is equal to the imaginary part of w rescaled. Right? So the imaginary part of z, so the z variable goes to t plus delta t, so t plus delta t. Okay? So we take this metric, these definitions of the variables here, okay, and find the metric in terms of w and w bar. Is this clear? Okay, so shall I work it out? Okay, it's the same exercise we did last time. Okay, so if we want to work it out, we would get d rew the whole thing squared, because that hasn't changed, plus t plus 2 delta t. Okay, so just 1 plus 2 delta t by t for the first order, d im w. Is that clear? It's substituted. So the change in the metric is what? So delta g is, we have delta g imaginary is equal to delta t divided by t, and that's it, right? But now we can translate that into gzz and gz bar z bar. But gzz, some linear combination of the real and the imaginary part. There's no change in the real part. So the change in both gzz and the change in gz bar are proportional to single modulus in the game. What we have to do is to find integral d to z or w doesn't matter, b times dgz bar z bar by dt plus B bar times del G Z Z by D. Okay? Now, in this insertion only the zero mode matters. On the zero mode, B is equal to B bar, and each of them, this whole thing, and they're both constants, B is equal to B bar, they're both constants. So this whole thing can be written as the volume of this thing times, okay, so what? So it's D2Z times B of 0 times 1 by 2. Up to factors of 2 become. Is this clear? But this D2Z is pi into T. It is added some pi's into T. So this thing is proportional to V of 0 without any factors of T. The volume of the strip. Okay? So the B insertions have just B of 0 with no factor of T. That was the same as in the torus view, if you trace that. No, okay, two copies of it. Should be a little careful, but okay. However, what about the C insertions? We play the same game with the C insertions that we did last time. Okay? We have just one unfixed conformal Killing vector. It's the same thing that we said for B's. Because there was a C and a C tilde, it's both constants, but now C is equal to C tilde. So one conditions. Okay? The one unfixed conformal Killing vector is translations along this direction. Okay? And we could, fixing that one unfixed conformal Killing vector, is like choosing one boundary operator to be fixed. But we can, because the insertion point of that C doesn't matter, because C is a constant, the zero mode of C is a constant, we can separate where we put that C and where we put the integration vertex operator. And then integrate over the vertex operator up to a division by the volume. Okay? So, the net result is that instead of having the fixed vertex operator, we can have all vertex operators integrated, but with an insertion of C0 divided by volume. And the volume is C. Okay? So the final conclusion is that we have dt divided by t, expectation value of b0, c0, times whatever, or times the integration vertex. You know, this, you see where this 1 over t came from. Where this 1 over t came from, it's actually very intuitive. You see, there was one gauge invariance that was left unfixed. The gauge invariance was translations around strip direction. Okay? Now, so because the volume of this translations along strip direction is finite, we could forget about fixing it. That's what we're saying there. We're treating all vertex operators as integrated. But in forgetting about fixing it, we are treating gauge equivalent configurations as distinct. Now each gauge equivalent configuration gives us the same answer, but we have the volume of the gauge operator. Okay? So if we just treated every vertex operator as integrated and forgot about fixing, okay, then we would be overcounting by a factor of the volume of the unfixed gauge. Okay? That volume is t, so we have to divide it. Okay, so that's the intuitive reason for this 1 by t. The intuitive reason for the 1 by t again. Okay, so you need a b0 and c0 to make any sense, and this is the unfixed gauge index. Is this clear? So remember, this is the answer for the open strings, and the answer for the closed strings was d2 tau by mu tau, and b0, b bar 0, c0, c bar. This is closed. Okay, time to again interpreting. Okay, so now let's move on. What we're going to do now in the rest of this class is to actually evaluate the closed string partition function and the open string partition function for the simple theorems we can study. Okay, and then interpret these objects. Okay, these calculations will show us some of the basic properties of string theory at loop order. Then a sort of qualitative thing. Okay, so we've done this closed string thing before, but just quickly to remind you of it and to remind you of the interpretation. Okay, so what do we have to put in here? We have to put in the partition function of the BC system. We have the partition function of the X conformal field theory, and that's it. So now let's write down the partition function of the X conformal field theory. The partition function of the X conformal field theory was what? It was 1 by mu tau to the power 26 by 2. So let me just write it, the whole to the power of 26. Okay? Then we had 1 over q to the power minus minus 24 minus 1 by 24. 1 minus q to the power n, product over n, 1 over q bar to the power minus 1 by 24, product over n, 1 minus q bar to the power n, where q is equal to e to the power 2 pi. Okay, that's right. Check if tau is I times something, it should be negative. So that's yeah, so that's okay. Okay, now somebody help me understand this expression. I time factors, and then this whole thing is raised to 26. So somebody help me understand every term in this partition function here. Okay, let's start with the in tau part. Wait a minute. No, I'm saying, okay, let me say what this is. This is just Z matter. Yeah, Z matter on a torus of moduli of modulus is equal to this. Okay, we're not integrating over any modulus. This is the partition function of the matter conformity theory on a torus of modulus tau. Okay. So firstly, give me a Hamiltonian interpretation of this partition.
it's somewhat oscillated.
Yeah, the Hamiltonian interpretation of the partition function on the torus is that of a trace over the spectrum of the conformity. Is this clear? Is this clear? Does everyone know this? We discussed this last semester and this is basic quantity theory you should know, but somebody explain this to me. You know, how in path integral language do you compute the trace over a trace e to the power minus beta h? You do the Euclidean path integral on what manifold? A space across a circle and the size of the circle is beta. Right? Is this clear? This is familiar. Okay? Good. So now, suppose we have a rectangular torus. Suppose we have a rectangular torus. Okay? Then, what would the path integral, so this is 0 to 2 pi, this is 0 to 2 pi tau. Okay? What would the interpretation, the trace interpretation of this path integral be?
It will be part z of something with tau, 2 pi tau with beta.
Let's call this 2 pi t because tau. Okay, sorry, yes, one.
2 pi t is beta and it is living on a circle.
Right. So let's say that we take the system as to be living on a circle of size 2 pi. So it would be trace of e to the power minus 2 pi t times h. Okay. Now if we make this torus cube, now we have a suggestion for a path integral, for a Hamiltonian interpretation. So let's call this the interval. You see, instead of just translating in time, we've also translated in space. So how do you get this skewness? You put a generator of translations at the last step of the path integral. You do a trace up to a generator of translations. Okay? So what is the generator of the translations? And leave it up by 2 pi times the real power. Okay? So you want an e to the power 2 pi times the real power tau times an I, because that's what generates algebraic momentum. And then P, the generator of translations. But H is L0 plus L0. Okay? So this was L0 plus L0. And this was L0 minus L0. Now let's combine it together. So look at the terms of proportion, which are the L0. So this is e to the power I times 2 pi times tau L0. You see? Times e to the power I 2 pi tau bar L0. Okay? So the Hamiltonian interpretation of the partition function of the torus of modular parameter tau is this object. And this is what we've chosen to call q to pi 0. This is what we've chosen to call q bar to pi 0. Is this clear? So this is the thing we have to calculate. Okay. Now help me understand where each of these terms come from. Okay, so let's do the easy thing. What is this 1 minus q to the power? Let's back up. Exactly. So the oscillators. What is the spectrum of our system? The L0 spectrum is a spectrum of oscillators of frequency 1, 2, 3, 4, 5. Each oscillator, an oscillator of frequency m as partition function, 1 over 1 minus e to the power n. Yes, the occupation number of the oscillator. So we've got all of these oscillators and we have to take the product. Is this clear? Okay? The q bar was the same thing. Now what is this q to the power minus 1? There you go. It's the fact that we have to take it out the 0 point. 0 point anything spent a long time discussing earlier. Has L0 equals minus 1 by 24, L0 bar equals minus 1. Very good. And what about this in tau to power?
Just a part of the d squared tau.
D squared tau.
I mean, d squared tau by in tau.
No. That came from the measure. Here I'm just talking about the partition function of the boson itself. Here just the partition function has this term. Maybe we should examine. We should suggest a date to this exam. When do you get like? Well, let's say end of. This is September, right? Okay. Last week of October we're having an exam. All of Kunchinski volume 1. Okay. And I'm going to be very disappointed if you guys don't know all the data. Okay, please stand. Right? Yeah. Okay. We've accounted for what? We've accounted for the oscillators. What is there apart from the momentum? It's the zero mode. Right? The zero mode is what? The zero mode behaves like a mode. Remember, it was 1 over 4, we have 1 over 4 pi, as alpha prime, okay, times x dot squared, 0 mode squared, times a factor of 2 pi. Okay, so there's this part of the Hamiltonian of the problem that we're not yet there. Okay? Now, in dealing with this part, it's easier, it's better to use this form of the expression for the Hamiltonian than this form, because 0 mode not 2 both pairs 0 and 0. Okay, so that's only Hamiltonian not 0. Okay, so we have to calculate trace of. Okay, so what's the spectrum that does? The spectrum, so what's the Hamiltonian firstly? The Hamiltonian is, that comes from here, is p squared alpha prime by 2. P squared by 2n. This is exactly the Lagrangian for a non-relativistic particle of mass m, where n happens to be 1 by alpha. Is this clear? And I've written down here p squared by 2n. So this is the spectrum. So what we want to do is to compute trace of e to the power minus alpha prime p squared by 2 times 2 pi in tau. This is what we want to do. Now what is this? Give me an expression for this trace.
This is integral of these are Gaussian integrals.
Exactly. So this is integral dp e to the power minus alpha prime squared p squared by 2 pi in tau. Because this trace we do in momentum basis. We use the fact that we've got completeness. Yes. Okay? And now we've got a Gaussian integral. From that we get 1 over square root tau. Now all these other factors that Kunchinski has that we haven't bothered to keep track of. I think we've done them correctly. But we're not bothering you. So that's where this came from. Is this clear? Okay. Fantastic. Now, so this was the matter partition function for the closed strings. here, let's simultaneously write down the matter partition function for the open strings. Or maybe it's, okay, let's finish the closed strings with your open strings. Okay, good. Now what about the ghost partition? Okay. Now something we can say about this partition function immediately. Okay? Something that we can say immediately about this partition function is that it is modular invariant. Okay? That is, z, for instance, it implies that z of tau is equal to z of minus 1 by tau. Or more generally, it's invariant under full modular group. Okay, we discussed this modular group, this SL2Z modular group last semester. I won't describe it again. But why is that? Okay, that is because this is a conformative theory. Okay, so the partition function is invariant under scalings. Now, a torus of modular parameter tau is equal geometrically to a torus of modular parameter minus 1 by tau up to an overall scaling. And the partition function is just invariant under that scaling. As we discussed great length last semester. Okay? So, while it's not obvious algebraically, we get a very interesting property of this function. Okay? So this function that's defined by this in tau to power half, the product of q's and this product of q bars, okay, is invariant under tau goes to minus 1 by tau. Okay, this is something we use when analyzing the open string spectrum in a little bit, so I just want to remind you of that. Okay, fine. Now let's return to the ghost business. Okay, so what is the partition function of the ghost thing? Now I'm going to tell you, I'm going to once again write down the answer and ask you to help me and figure it out. It's q to the minus 1, q bar to the power minus 1, q bar to the power minus, what is it, 26 by 24, and then product of n is equal to 1 to infinity, 1 minus q to the power n squared, 1 minus q bar to the power n. I'm claiming that this partition function was a B bar C, C bar insertion. The ghost part. Ghost is equal to this. Okay, help me figure this. Where do each of these terms come from? So firstly, where are these? Come on, people. Somebody. Come, where does this come from? So once again, it's q to the power L0. So it's a spectrum of L0. So where do we get this from? What are the modes of the C and B and C? Ghosts. Up. Part of the reason you're not getting it right is that I said it wrong. Let me get it right here. This should be in the numerator. Sorry. Sorry. Okay, so let me remind you. So the B and C system had oscillators just like the X thing, starting from 0 to infinity. But B and C's were anti-commutative. So the occupation number in each oscillator is either 0 or 1.
But it's an extra minus sign because they're both.
There's an extra minus sign because what are we computing? We're computing the partition function with periodic boundary conditions for B and C. Okay? Why are we computing with periodic boundary conditions? Because they were ghosts for diffeomorphisms which have periodic boundary conditions. Or the moduli which have periodic boundary conditions. Okay? But the Hamiltonian interpretation of the path integral with periodic boundary conditions for a field that is anti-commuting is traced with an extra factor of -1 to bs. Okay? So what we're computing is not trace e to the power minus beta h. We're computing trace of e to the power trace of -1 to the x times e to the power minus beta h. Okay? So this is the vacuum. No oscillator excited. This is the state with one oscillator excited. Since it has opposite fermion number from this guy, it has one extra anti-commuting field excited, it contributes to the minus. It's a numerator which says that there are only two possible states. Occupation number 0, occupation number A. Occupation number 1. Is this clear? Okay? It's squared because whatever we have for C, we also have for B. Okay. Now, in the 0 mode sector, had we not had these extra insertions of B bar, C bar, we would have got 0. Because the 0 mode sector has this two-state system with opposite fermion number and the same energy. So the trace with -1 to the f would have given us 0. But these insertions help us pick out these. There's one two-state system for left movers, one two-state system for right movers. So the four-fold degeneracy in the 0 mode sector. These insertions help us pick out exactly one of those four states. Okay? And we don't get 0, no more cancellation. It's the state where which omits 0 and start signing to 0. The physical state. We discussed this last time. It involves knowing the right scalar product in the sector. I won't get into it. But okay, so fine. So we have this. Now what about these extra factors? What about this q bar to the power minus 26 by 24? Which will be plus 26. Maybe I'm sorry. Maybe just 1 minute. Here, I'm sorry people, I'm getting lots of excited. So I should have ground state q to the power energy. Yeah, it's q to the power energy, and energy. I should have had q to the power energy, and so this is the numerator. Let me just get sorry. Yeah. This q was with -1 by 24 was in the numerator, or downstairs in the denominator. With a +1 by 24. Because the ground state energy was -1 by 24 in the latter sector. And we're calculating q to the power energy. Okay? So this q was in the numerator. Sorry. Okay? Now here we will have here I can get that correctly, but let me write it down. I'm sorry, let me write this whole formula down. This will be q bar to the power -1 times q bar to the power plus 26 by 24 times product over n 1 minus q to the power n squared 1 minus q bar. Alright. So this is Z cos. Now tell me what this factor is. It's the same as this factor. Just explain that statement to me.
Because with the cos there is no weather. Okay. There is no 0 point here.
Right. Every conformal field theory has Casimir energy. You see, the vacuum, the identity operator, has dimension 0. So that 90 translates into the vacuum having energy 0. That statement is 9 because it doesn't account for the conformal element, as we discussed last time. And the correct version of that statement is that the energy of the state corresponding to the identity operator is minus C by 24. In this case, C was 1, so that's minus 1 by 24. L0 was 1. Minus 1 by 24, L0 bar was minus 1. Minus C by 24, L0 bar was minus 1. Minus C by 24.
26.
Everything is to the power of 26. Okay? What is the central charge of the BC system? It is minus 26. You know that because that's how we got the critical dimension, right? The full conformal field theory had to have central charge 0. Matter had central charge 26. BC system had central charge minus 26. Okay? So this is the energy of the state corresponding to the identity operator minus C by 24. C is minus 26, minus 10, so plus 26. Is this clear? Finally, what is this? The what? Okay, it's, yeah, sort of the 0 word, but it's not. You know, this is not a numeric field. It doesn't have the usual sort of 0 word. What is the difference in this theory between the vacuum and the state corresponding to the identity operator? Do you remember the state corresponding to the identity operator was not the same as the vacuum of the theory? The vacuum of the theory, in fact, was C, was the state corresponding to the operator C. Okay? And since C has dimension minus 1, the vacuum has energy minus 1 compared to the state corresponding to the identity. That's this. All these oscillators are counted above the vacuum. We should be writing that together, the energy of the vacuum. And we've done that correctly. Minus 1, minus C divided by 24. That's the energy of the vacuum. Is this clear? Okay? Yeah, okay, we've gone slower than I hoped today, but anyway. Okay, so now let's put all this together. We have to multiply this guy with this guy. Okay, so these oscillator factors of the 26, 2 of them go away. Okay, what about these other factors? You see, this and this cancel, but this remains, and this is exactly enough to be a q to the power plus 1 by 24 in the denominator for each of these factors. Okay, so let me write down what remains. What remains is 1 by d tau times 1 by q to the power 1 by 24 product over n 1 minus q to the power n product of q bar, say product of 1 minus q bar to the power n times square root of m tau the whole to the power 24. Exactly. This is the partition function of this 24 was. In the light bulb, we would have kept the 0 modes in all 26 directions. Apart from in tau factors, this is what we were going to do. Okay? Yeah. But if you actually take this extra in tau, it's exactly. Okay. And then we combine this together with the measure of a moduli space we have in the torus. That was d2 tau over in tau. So that becomes d2 tau over in tau, the thing squared, times whatever is in the bracket. Okay? So this is our final expression for the partition function over the torus. And we were very happy with this expression, if you remember, because we wanted this expression to be modular invariant. And we checked that d2 tau over n tau squared was a modular invariant measure. And, of course, this is modular invariant. That we just answered. Because whether it's power 26 or 24, it's modular. It's the same thing that we have there, but to power 24. It's the partition function of 24 bosons and the torus. So we got a very nice, we had this very nice modular invariant answer for the partition function of closed strings and the torus. Okay. Now, okay, this is really nice. Now the thing that we want to do is to physically implement this. Okay? So, what is the partition function in string theory? But in field theory, suppose you calculate the partition function. Okay? Suppose you calculate the partition function with no insertions of vertex operators. What you're getting is a correction to vacuum range. Okay? So, we might think that, well, in this problem, we know what the correction to vacuum energy might be. It must be if the modes of the closed string are governed by field theory. Okay? So let's compare this answer to what we would get by summing over the vacuum energy graphs of all the particles of free string theory. Okay, so that's the exercise we have to take. Okay, so suppose we had a particle of mass m, scalar particle of mass m, and we want to calculate its contribution to the we want to calculate its contribution to this vacuum energy business. We want to calculate its contribution to vacuum energy. We want to calculate its contribution to the vacuum energy of the theory. Okay? So what do we get? What we want is to integrate dgk of log of k squared plus x. Right? Because status. Well, I mean, the easiest way to say it is there is this graph. And that graph represents just that logarithmic term. But a more physical way to say it would be to, okay, I'm just going to, can we move forward from here? This, if you were to accept that this graph is just that long.
But there should be prefactors to
Prefactors of
depending on the speed of the...
It'll be the number of degrees of freedom. Okay, suppose we were doing just a scalar particle, it would be exactly this. And if we had additional, let's say a vector particle, it would be multiplied with the effective number of degrees of freedom. Okay, that's always how it works in a 1D. Okay? So we're going to be a little naive here. That's a true statement. We're going to be a little naive here and just sum over all effective degrees of freedom. Okay, so this calculation is correct just for scalar particles. it's true actually for every kind of particle if you multiply by effective number of degrees of freedom. The statement I'm making. Okay, now this effective vacuum energy graph, okay, can be related in a sort of prettier way that helps us make contact with what we have in string theory. Okay, and that way is to rewrite this in the following way. To rewrite this as dt by t times exponential of minus t, and for fun you put it 2 here at the level at which we are working, ignoring factors that doesn't matter. Dt by t exponential of minus t by t squared. Okay, why is this true? Well, you see that suppose you didn't have this t here, then this answer would be proportional to 1 over square root of a squared plus x squared. Okay? Times sorry, no square. 1 over a squared plus x squared. Okay? Now integrate both sides with respect to k squared plus x squared. Okay? And that gives you 1 over t here. Okay? And there's another way of saying it. Actually, the statement is a bit careless because this integral is not really well defined. You have to define it with respect to some cutoff. But if you put some cutoff here, lower cutoff epsilon, another way of saying it is the following. Another way of saying it would be another way of saying it is that if you look at the formally this object is independent of k squared plus x squared by change of variable. And you can define some p prime which is 3 times k squared plus m squared. This measure is invariant. Formally, this answer does not depend on k squared plus m squared. Okay? But the reason that it actually does is that there's a cutoff here. There's a divergence at small t. You have to cut that cutoff. That cutoff state to be very small. The dependence on the cutoff is clearly logarithmic. And when you make this change of variables, you change that cutoff by this factor of k squared plus m squared, and that's the origin of this log. So that's the second way to say this. Yet another way would be that without this t, the fact that this is 1 over k squared plus m squared is dimensional analysis, and the same dimensional analysis that makes it a log with it. This is all equivalent. Okay. Now this is very useful represent. It's a little careless. There's something you have to deal with cutoff and so on and some subtraction. But let's just hold it. Just forget about all those things which we can deal with. Okay. So now this is a useful representation, and it has an interesting interpretation. Suppose we were interested in looking at the theory in first quantized language. Okay? Then this is the sum over all particle products. T is the modulus of that surface, the length of that path. dt by t is the sort of measure that you would have calculated by the analog of all the processes that we've been dealing with for string theory. And this is simply the fact that you're computing the trace of the Hamiltonian weighted with the effective temperature of this quantum mechanical system, the effective temperature is T. Okay? So from the point of view of first quantized language, this is very natural. Okay? And that makes it clear that this is the right expression to use in comparing with the string theory, with our string theory calculation. Because it makes it clear that it's the right expression to use by comparing with our string theory calculation because the string theory we're working effectively first. Okay, fine. So now let's so what would we expect from this point of view the vacuum energy of our string theory to give us? What we will expect is that we will have dt by t exponential of minus t by 2 into k squared plus mi squared with some I over all the particles string. sum of the particles weighted by effective degrees of freedom. So better to say, we should sum over all the states of the physical states of the conformal field. Each of those gives you some polarization of the right particle. Okay? Then it deals with the orientation. Okay? Now, how do you relate mi squared to something in world sheet conformal? Well, remember our Marshall formula. Our Marshall formula was that alpha prime m squared by 4 was equal to L0 minus 1. But that was also equal to L0 bar minus 1. So we can write this as alpha prime m squared by 2 is equal to L0 minus 1 plus L0 bar minus 1. Where L0 now is pure oscillator. We've taken out 0 point divided by 2. Oh, sorry, below. I removed the 2. And twice alpha prime m squared by 4 is equal to this. Okay? So, you see that the now, to every oscillator state of L0, there corresponds a particle in string theory. The mass is given by this formula, but there corresponds a particle only to arbitrary oscillators on the left and on the right, but subject to the level matching relation. L0 is equal to L0. Okay? So, if we want to do the sum over all particles in string theory, weighted by their mass, is a very clever way to do it. The first thing we'll do is to replace t by a tau variable. So, t will call alpha prime tau, so that there's an alpha prime. Okay? So we get integral d tau by tau, that hasn't changed. Then exponential of minus tau alpha prime k squared by 2. That will take out. So, times exponential of minus tau alpha prime m squared by 2. Okay? But now the sum over all particles or independent polarizations. But that sum now will be replaced by trace over the worldsheet Hamiltonian, and we'll replace alpha prime m squared by 2 by exponential of minus tau L0 minus 1 plus L0 bounds. Okay, now by abuse of, I'll call this T again. It's useful for me to have a T. Start with complex things. So, just reschedule. Okay? And then the whole thing is dt by t. But this is not quite right because it individually traces over L0 and L0 bar without implementing level matching. So we must implement level matching. We must put a delta function saying L0 is equal to L0. But the eigenvalues of L0 and L0 bar are both integers. It's very simple representation of the delta function with integers over the whole space of integers. We multiply this by d theta, integral over theta lives from 0 to 2 pi, and multiply exponential of I theta into L0 magnitude. That's the delta function that says L0 is equal to L0 bar and enforces level matching. Now this is exactly what it is. Is this clear? Okay? Now let's define a new variable, tau, which is equal to theta plus I times c. you see that this gives us q to the power L0, q bar to the power L0 bar. Okay, we have q bar to the power -1. Where's the -1 step? And we also have, we could write this as L0 -1 minus L0 bar minus 1. Okay, and then we can do the integral over k and get our in tau. It was t, but t was in tau to the power 1, 13 by 12. Okay? So, this thing is just d2 theta, d2 tau, d real tau times d imaginary part. No? Okay? This was imaginary part of tau. So we recover exactly what we had in tau. Exactly what we had before. Right? We recover exactly what we had before, except for one important change. If we have d2 tau by in tau, now this in tau, this is in tau to the power 13. So this is squared, and then we put 12 in there. So 1 by square root in tau times q to the 1 by 24, q bar to the 1 by 24 times this prop. All to the 24. Right? This is over 24 because we were doing this in light code gauge. So in light code gauge, we have the light physical spectrum and then we have to impose left magic. Okay? So we get exactly the same expression that we had before, except for one change. Can you ever tell me what that one change is? The change is in the region of integration. In string theory, you integrate tau over all inequivalent tori. And you remember from last semester that was tau from -half to half in the real axis times the exterior of the unit circle. So the region over which you integrate is this. The fundamental domain of the torus, the set of all inequivalent tori, the set of tori that are not equal to each other up to a modular term. However, in this field theory calculation here, what you get is the integral over the whole upper upstream. Because theta went from 0 to 2 pi, or if you rescale theta by 2 pi, it went from -1, 0 to 1, or -1 and a half, doesn't matter. That's the same region. And t went from 0 to infinity. Remember, in our original integral, t went from 0 to infinity. So that's the source difference. Okay? So apart from this change in integration domain, we got exactly the same ones. This change in integration domain is actually very important. It's actually very important for the following reason. You remember from our field theory calculation, the part of the calculation that was sensitive to UV divergences was large K. Now large K transmutes to small t. Why is that? It's because we had this e to the power minus t times k squared. So the only way that large K can contribute is if t is very small. Otherwise, large K is exponentially suppressed. Okay? So the part of the diagram that corresponded to UV divergence of field theory was small t, and it's present in the integration that field theory logic seems to give us, but it's absent in the integration according to the rules of string theory. Now, you are thinking, this is a bit of a fail because I happen to choose this particular modular domain. I could have chosen this domain. Okay? In that case, we would have had a small deviation and a potential divergence. But you see, all domains are the same. So let's trace up what we're saying. What is this point under the modular transformation? The modular transformation that takes us from here to here is calculus of 1 vector. So this point maps to infinity. Okay? So, what you're saying is, well, you're not worrying about the problem here, that's thrown away, but wherever you had, there's a reflection of that same problem once you go up there. So what about the problem at large t? Now remember, the problem at large t, the only values of k that contribute are very small values of k. So this is one of the great things about string theory. You see, if you have a problem at large t, it means that there must have been in field theory language a problem at very small values of k. Or restated, if there was no problem at very small values of k, and as long distance in field theory, there cannot be a problem at large t. So now what I say is that string theory links good IR behavior to good UV behavior. Let's see this in more detail. Oh, we have to run this screen. Yeah. Just 1 minute. Let's see this in more detail. You see, let's look at this partition function. Let's look at this partition function at very large values of t. Okay? At very large values of t, only the ground state contributes. The ground state in this particular problem had negative energy. Okay? So what I'm saying is that you take this partition function and expand it in a power series expansion. I mean, a power series is an e to the power minus t. Okay? And you get an e to the power 2t, that's the ground state, plus 1, that's the zero mass center, the contribution of massless particles, plus exponentially suppressed. And we have to do the integral d2. So let's forget about theta direction, which is the t direction. So dt over t squared. And if you remember, we have t to the power 32. Yeah, it's okay. It's just t to the 12 32 t squared. So dt over t times t to the power. Now this guy clearly gives us a problem. It blows up exponentially at large. So we, in the Bosonic string, the one-loop partition function for the Church string is divergent. That's true. But why is it divergent? It's divergent in large t, which means it's divergent in small k. One must call the divergence. This is a tachyon. You see, it's coming from the ground state of the string, which was the tachyon. Basically, if you've got a state of negative energy effectively on the string, okay, that's going to give you a divergence. Okay? Now, why field theory terms there divergence of the tachyon? It's because we are trying to do a path integral of e to the power plus m squared phi squared minus k squared phi squared. So if k is smaller than m, these modes, the amplitude for the modes at k smaller than m want to grow rather than, the path integral is maximized by these amplitude modes being very large rather than being very small. And that gives you the divergence. That's the divergence we're seeing. We see the fact that if you take any negative mass particle and try to do perturbation theory, okay, you get a divergent contribution to everything. And this is an infrared divergence. It comes from k smaller than m. It's an infrared divergence. So closed string theory does have this infrared divergence because it has a tachyon. That we knew. However, in the absence of the tachyon, suppose we managed to make a string theory where there was no negative mass state in the conformal basis, no tachyon, then this onwards is finite. This is an algebraic finite. finite, and this is an exponential. Okay? Now, when we deal with the superstring in about a month, we will construct a string theory which has no pattern. So, we won't have to make this apology about infrared behavior. The ultraviolet thing, you can always view the path of the angle in a way so that the ultraviolet region is just not there. Okay? All possible problems are infrared. And if we know that the theory is well behaved in the infrared, then it is automatically guaranteed that we will have no divergence problems in our one loop. Okay? So once again, just look at the connection between string theory and field theory. String theory, for this particular question of calculating the vacuum energy, does something very smart. It cuts off effectively high momentum regions. Now, you see, there's one last thing I want to say before we go to global, and that's this. You might think that, well, that's sort of easy. We just put some cutoff in momentum space. Somehow, that's what string theory seems effectively to be. It's like we could just do that by hand, and any old cutoff will do, and we get some sensible results. I want to emphasize that that's not true. That's not true because, one thing that I want to emphasize is that under tau goes to 1 by tau, you see, these points are invariant under tau goes to 1 by tau. This is the boundary of what's linked by tau. And in particular, a point here is mapped to the point here. So let's look at the topology of this space. This thing looks like a strip with boundaries. But actually, this edge, this thing, is the same as this thing. So it's a cylinder, and this part is the same as this part. So you see, it's like a cylinder whose edges have been stuck. Okay? At infinity, every point at infinity should be thought of as the same point. When it's going to be used. So what this is like a sphere. The topology is like that of a sphere. This fundamental domain here is a compact manifold. That's very important because you may remember from last semester that all our no-ghost theorems, the fact that BRST equivalent amplitudes, BRST equivalent operators gave us the same amplitudes, okay, relied on there being no total derivatives in moduli space. BRST equivalent operators gave us equal amplitudes up to total derivatives in moduli space. If there are boundaries to moduli space, these total derivatives are contributed. If BRST equivalent objects give you different amplitudes, you have negative norm states in your theory, and your theory breaks you down. Okay? And this is the problem that has plagued every previous attempt to quantize reality. You try to put a cutoff by hand, it's very hard to do that in a way that does not break the cube of invariance and therefore introduces negative norm states in your theory. Okay? String theory has a very clever way of putting this cutoff in a way that preserves unitarity. If you violated this in any way, if you chose to integrate over some other part of the fundamental domain, you will introduce negative norm states in your theory and the theory will make sense. It's a very particular way of cutting off the theory that manages to make sense. And this is a very important point. Okay, I hope to discuss the open string also, but clearly we're not doing that today. That's one